Hey everybody, Philip here. So I've been taking field recordings recently, which I think is really fun. It's a really nice way to just be out in the world, doing something, out in the world, doing things with sound. It's making me listen very carefully, which is so cool. Like I have such a better attunement to the place that I'm in. When you're like, oh, there's a helicopter over there. I'm going to try to get away from that so I don't hear it anymore. And you really, when you live in Los Angeles like I do, you just become acutely aware of how many motor vehicles there are everywhere. They're unavoidable. But here's a recording I took at the skate park. So what I was thinking I'd do in this video today is just try to do some experimental sound design with this particular sample in Gen with MC and just see what happens. So let's do it. So I'm going to start out with a buffer, a container for this sound file. I'm going to call it skate park. I'm going to make a drop file object so that I can just drag and drop whatever sample I want into this max patch, and I will say prepend read, and then patch that into the buffer. We'll also create an info object while we are at it, which is going to give us information that we need from this buffer, such as its sampling rate, which it'll give us from this first outlet here. So I am just going to drag and drop from my file browser. You can see that we have a stereo file here, and it's at 96K. And then I'm going to make a waveform so that we can look at it. And I guess we should look at both of them. There's like a channel offset. Yes, there we go. So that's both of them. Actually, we don't only need one because they look the same basically. And then if I click and drag on this, I guess I need the little B patcher here. This is a little UI you can get from the waveform object help patch. You can click and drag to select a region, which we get from these two outlets here. And this is in milliseconds. Ultimately, when I'm playing back this sample, I'm going to be doing it in Gen, and I really want this number to be in samples. So what we'll do is just convert this from milliseconds into samples. Now, I cannot use samps to ms in this case, or like translate object here, because those are going to use, as the sample rate, whatever my computer's using, which if I open up my audio status is 44,100. kilohertz, but this sample is at 96K. So if I combine together the two numbers that I get from the waveform object here, and then I'm just going to use a vexper object to sort of mathematically figure out what the start and end point are in samples rather than in milliseconds. So the first thing that I'll do is take that millisecond value, I'll divide it by 1,000 to turn it into seconds, and then I will multiply it by the sample rate value of the file. And I'm going to use scalar mode 1 here because I'm going to pass just a single float into the second inlet here. So now I need to tell it to give me that number. There we go. And so now these two are in samples. So now if I create a gen patch, its name is going to be playback. It's going to have two channels. It'll be mc.gen, so it's two channels. That's good for now. And then inside, I'm going to create a buffer. And I like to call my buffers inside gen buffer name And the reason is that you can then do this, buffer name skate park. Kind of just a handy way to, like a convention I like to use, okay? And we can check to make sure that we're getting the right data here by just checking to see, is this telling us that skate park has two channels, which it does. So now we'll create some parameters. So we'll do start samps, and then we'll do end samps. I don't know, just start with 10,000 samples by default. Or how about, yeah, whatever, 10,000 is fine. And then we also want param sample SR, which will be the sample rate of the sound that we have in the buffer. So we'll start with 44,100 as the default, but we know that we're going to be changing that. So now if we send this message sample SR with our actual sample rate and start samps with the first value and then end samps with the second value. And then we'll just bang and make sure that stuff gets sent. And then I'm going to want to do some playback. So basically what we're going to do is we're going to play back by creating a signal that tells the peak object which position in the buffer it should read back. So we'll say, we'll use peak, we're going to read from this buffer that we have that's called buffer name, and we're going to use linear interpolation. There's many objects that can read from buffers. There's peak, there's wave, there's so many. A lot of them are actually the same under the hood. They just have different sort of qualities that can be overridden by setting these arguments. But in this particular case, I basically just want an object that will allow me to take from its first inlet some index, some position within the buffer in samples. And then I want to make sure that it actually does perform linear interpolation so that when it's playing through multiple samples, it smoothly interpolates between them. You can read a lot more about this kind of, how this kind of stuff works in Go, where there's some really cool abstractions that allow you to read back samples in very sophisticated ways that limit aliasing, just as an aside, but we're not going to worry about that today. So we have this object that's going to read from the buffer. With it unconnected like this, we're just going to be continually reading the first sample of the first channel of this buffer. And we know that we have a 2-channel buffer here. So what we want to do is basically make it so that the odd numbered channels read from the first channel of the buffer and the even numbered channels of the MC patch read from the second channel of the buffer. Right now we only have 2, so there's only 2. But if we wanted to increase this number of channels in our mc.gen, which, spoiler alert, we will, then we're going to want to just say odds and evens. So MC channel, this object inside of gen is going to give you the channel index, so which channel we're currently on. So if I send this to the outlet, and I take an MC number here, we have 1 and 2. So we'll subtract 1 from that. And then we'll take the modulus of 2, which I believe it should give us the same result. And so now then, like if we had a 4-channel MC, 4 MC channels, then we would, the first and the third would read from the first channel of the buffer, and the second and the fourth would read from the second channel of the buffer. So that's great, and that second inlet here of peak tells us which channel we're going to be looking at. Great. So now we need to basically make an accumulator that's going to kind of count up sample by sample to cause us to read back from this buffer. And the simplest way to do this is to just use a wrap object where we're going to be counting up one by one, wrapping from our low to our high, our start and our end points. And we're always adding the output back to itself. So this is how we kind of build an accumulator or sort of a running total machine. And to start, we're just going to add one sample each time. And now if I do an MC live gain over here on the output so that we can turn it up and down. And then MC DAC, 1, 2. So now that's connected and we should get playback. Hopefully we do. We did. But there's one thing that's weird, which is that the pitch is super low. Like if I play it here, and then I play it here, this is super low. The reason for that is because this is a 96 kilohertz sample, but my computer is only running at 44,100 hertz. So this adding one sample for each sample frame that passes is basically half-ish the speed that we would want to be reading through this sample in order to play it back at the correct speed. So what we need to do is basically adjust the rate at which we're moving through the sample according to the sample rate of the sound file. And so that's why we actually take in this sample rate from the info object, because we can't get that inside of Gen, so we just have to pass it in from the outside. So what we're going to basically do is divide that by the output of that param by the output of the sample rate object, which is this is going to be the computer's or Max's sample rate. And this is the sample rate of the sound file passed in from info as a parameter. So we'll divide the sound file sample rate by the computer's sample rate. And this should give us a number slightly above 2, which it does. I need to get rid of this. Slightly above 2. And that's because 96,000 over 44,100 is 2.177. So now if we add that each time, instead of adding 1 each time, and we play back, sounds good. Okay, so now we have basic playback, and now what I want to do is kind of muck around with this. So one thing that I really like to do is basically kind of fool around with this particular signal that's being used to read back the contents of the buffer. And we can do this using a lot of the techniques that, for example, are in Go. What the book calls unit shaping, which is just this idea of taking a signal on the range of 0 to 1 and shaping that spectrum so that it's no longer linear. So you can do all kinds of things to it. You can make that kind of phasor-like shape. So let's go into MSP for a second. Phasor 0. Let's say 1 here. So like an example is using something like the twist object. And curving that line, right? And what something like that would do is instead of playing back at a constant speed, we'd play back at a speed that starts slow and then speeds up. Similarly, another way to do exactly the same thing would be to use, like, let's say scale with a fifth argument here that is not, and then this is where I think you have to do classic 0 or classic 1. Yeah, classic 0. Because earcam because old ear cam patches worked a certain way, everyone else has to write classic 0. Okay, so something like that. So in fact, we could do exactly that. So what I'm going to do is actually scale the range that we have here to the range of 0 to 1, and then we'll go back to the sample start to end range, just because it's going to be easier to work with 0 to 1. This is perhaps not the most efficient way to do things, but I think it's going to be just fine. So we'll go from start samps to end samps, and then 0 to 1. And then we can then do the opposite. So we'll do 0, 1, start samps. This plus object is a way to just like quickly grab a value that's stored under a param or a history in Gen. And then we'll go like this. So the space in between these two is kind of our like domain of unit shaping. We can do all kinds of weird things in here. So to start, I mean, a really easy low-hanging fruit here is just using the built-in curve functionality that's built into the scale object. So now if I grab this curve parameter, which is here, and let's send the shape to the output, to the second outlet, so we can monitor it. And if I now increase this to like 2.5, it's going to start low, at a low pitch. And you can hear that pitch is increasing because the playback speed is increasing. And then it goes back down low again. So that's kind of fun. And the way that scale works, if you're familiar with scale, you know, and there's a really nice, helpful little, so linear is 1, 2 is exponential like that, 8 is super exponential. I think that like 2, like 0.5 is like the inverse of 2. So like if you were to kind of, this is logarithmic, but it's like the logarithmic has the same base or whatever. Mathematically, they're related to one another. So I think what we can do is just say this is on the range of -1 to 1. The default's going to be 0. And we'll multiply by, well, let's just see what happens if we do. We raise the 2 to the power of whatever this number is. And we'll send it to the third outlet so that we can actually see what it looks like. So at the curve value of 0, we should get 1. With 1, we get 2. With -1, hopefully we get 0.5. In fact, we do. So maybe we'll scale this just a little bit. So we'll give it like times 1.5 or something. So that should give us some interesting shapes. And it kind of like, because if you use the object the way it is by default, it's kind of difficult to manipulate because the range of 1 to 2 is the same amount of transformation as the range of 1 to 0.5, which is, different in terms of the parameter value, but it's the same amount of transformation. So if we do this trick where we use this power of 2 with this exp2 object, which you can also use, is also very useful when you're working with pitch, which I'll actually show you later on, you can kind of linearize that range. So now if we pass that in here and then bring the gain up, so with a value of 0, we should get the normal playback speed. And I'm going to take a small part of this sample. Really small. Maybe we want a little more extreme here. Sounds like a kick and a snare, respectively. Okay, so that's cool. And then, so what else do we want to do here? So I think one thing that would be fun. So there's like a chapter in Go where there's like an LFO designer kind of idea, which is really cool. And basically like, it's just this idea of starting with a phaser, which is basically what we have here, just an accumulator from 0 to 1, and then passing that through like a set of stages of transformations. So one such stage, which is really easy to implement, is using this triangle. Where it like allows us to morph from a backwards phaser through a triangle to a frontways phaser. So min, max 1. So 0.5 is, I'm sorry, we don't want 0.5 as the default. We want 1 as the default because that's just going to give us normal forwards playback. And in fact, you know what? Let's flip it around so that actually we do the opposite. So we start with 0 as the default, because I think that makes a little bit more sense. So then if we take triangle and we go to 0, you can see we have a normal phaser here, and I'm going to grab a little short slice again. But if I go to 0.5, you can see that this is now forward and back, and so we can hear what that sounds like. Backwards, forwards, backwards, forwards. Cool. And then what if we combine it with this? That's very cool. Okay, then let's just do one more thing. So if we then scale this, so we'll scale by whatever. We can make a trapezoid. So we're going to scale it, and then we're going to clip to the range of 0 to 1, and then we're going to make a param that's called trapezoid, which will say scale 0, 1, 1, 10, let's see. And you'll see what happens here. This will make sense. But basically, we're just going to like multiply this triangle and then clip it so that it's still on the range of 0 to 1. So at 0, we just have the triangle. At 0.5, we have this trapezoid, which still has some of this curving. So I'll get rid of that for now. But then the result, that's kind of cool. seems like we need to scale this one a little bit too, because we kind of lose our range pretty quickly. So let's say, so this one we want the exponential shaping. So let's say 3. That feels pretty good. And I think this one's going to be really good when we have multiple of these, which let's do that in 1 second. But first, I want to give us the ability to change the pitch of our thing. I want to be able to transpose. So we'll make a param transpose from, I don't know, -48. So 4 octaves. Actually, let's do the transposition in octaves. And we'll do a similar trick here where we do exp2. So we'll raise 2 to the power of this number. And that's going to very conveniently give us kind of a multiplier for this slope that will basically make the slope shallower when the pitch should be lower and steeper when the pitch should be higher. So we're going to multiply here. Oops. Transpose. So no transposition to start. And we'll start with the default here. One octave up, 1 octave down, 2 octaves up, 4 octaves up, 4 octaves down, 3. Which, because I recorded at 96 kilohertz, sounds a little bit better than it would otherwise. This is pretty cool. Okay, now here's what we're going to do. We have these 4 parameters. What I want to do now is make multiple versions of this patch, so multiple MC channels where we have multiple stereo pairs. And then I want to be able to manipulate these parameters for each of those pairs independently. So the first thing, I'm going to do 8 channels. So I'm going to switch this 2 to an 8. Which means that we have 4 pairs of 2. And you see that we got this MC live gain now has 8 channels. We don't want that. We want this to remain a 2-channel output. So what I'm going to do is use this MC stereo object, which is an alias of the MC mixdown object. And basically what it's going to do for us is take an arbitrary number of input channels, in this case 8, and mix them down to 2 output channels. And then the right inlet here is for the panning. And basically, we're going to want to just preserve the original panning. So I'm going to use an MC list here with 0 and 1. And I believe that that should then, even though we have 8 channels incoming here, it's going to just say, I think it just wraps round robins around so that basically the odd channels go to the left channel, like the left stereo channel, and the right, and the odds go to the left stereo channel, the evens go to the right stereo channel, I think. So if we turn the gain up now, we should just get our original result. Great. And we don't have to change this gen patch at all. Now we just need to make it possible to talk to the gen patch for each parameter independently. And the way that we can do that is using this message called setValue. And the syntax of this message is basically you say setValue, and then you say the channel number of the channel you want to talk to, and then the parameter name that you want to change, and then the value of that parameter for that channel. In fact, I think the same syntax exists for the poly object. So we could do like multi-slider at size 4, because we're going to make one slider for each pair. Let's start with the triangle. So set min max 0 to 1. And then I'm going to want to turn this 4-item list into an 8-item list, where we have each item 2 times. And an easy way to do that is to just use zlace. So you can see we have pairs that are identical. And then we'll use the list funnel object, which if you've watched my videos, you've probably seen me use. It's one of my favorite objects. And then triangle. So the index, meaning the channel, and then the value. And we need to add 1 to the channel numbers. When we talk to Gen using set value, we need to use we start from 1, because I think 0 controls all of them, if I remember correctly. I'm pretty sure I'm right about that. So we need to do list funnel 1 so that we start counting from 1. And then if we use an MC scope here, we can now see all of the playback phasers. And if I then, now you can see these are all desynchronized from one another. By the way, small detail, if we're using the triangle, if the triangle is not 0 or 1, then we actually double the playback speed, because we're squeezing this like space that we play back the sound. We're playing it both forwards and backwards within that space. So I think we need to do a thing here, which is basically wrap the triangle parameter value between 0 and 1, which is going to make 1, 0. And so then we can say, we could just take the Boolean. So basically, if the value is 0, then we're going to play it at the normal speed. If it's 1, meaning it's anything other than 0 or 1 originally, the original value of this parameter is not 0 or 1. This is just a fancy way of determining that. Then we should have the playback speed, I believe. So we'll say times 0.5. Wait, let me think here. Yes. So we'll just do, if it's, that's what we want. And so then we'll multiply this. And I think we will need a history here. No, do we? No, we don't, because this is just a parameter. It's up here. All right, let's see how that sounds. Something's wrong. Let's see what we're producing here. Not out 2, out 3. Did I get too fancy? Oh, I think I needed to do the opposite of this. Because if it goes true, false. So this might still be wrong, but let's see. So that sounds right. That's right. That's right. Okay, great. Okay, so quick little workaround to work around an eccentricity in the triangle object. But now let's try what we were going to do. And then we can just add this same little editor here for everything.